Welcome back to JVM Internals Crashcasts. I'm your host, Sheila, and today we're continuing our journey through the core concepts of the Java virtual machine. We're in the first season, JVM Novice, and we're about to dive into a crucial component of the JVM, the execution engine. Joining me as always is our JVM expert, Victor. Hey Victor, ready to fire up this engine?
Hello, Sheila. Absolutely, I'm revved up and ready to go. The execution engine is where the rubber meets the road in the JVM, so to speak. It's going to be an exciting ride.
Great. Before we start, let's make sure our listeners are up to speed. We've already covered what the JVM is, its basic architecture, and we've talked about class loading, linking, and runtime data areas. Today, we're going to see how all of that comes together in the execution engine. Now, to get our listeners thinking, I've got a quiz question for them. Victor, what do you think about this one? What percentage of Java code typically gets JIT compiled during a program's execution?
Ooh, that's a tricky one, Sheila. It's not as straightforward as it might seem. The amount of code that gets JIT compiled can vary widely, depending on the application, its workload, and how long it runs. It's a great question to get our listeners thinking about the dynamic nature of the JVM's execution process. I'm curious to see what they'll guess.
Me too. We'll reveal the answer at the end of the episode. Now, let's start with the basics. Victor, can you give us a simple definition of what the execution engine is?
Certainly. The execution engine is the heart of the JVM. It's responsible for executing the bytecode that's been loaded into memory. Think of it as a factory assembly line that takes in raw materials, bytecode, and produces finished products, executed instructions. The execution engine has three main components: the interpreter, the just-in-time, JIT compiler, and the garbage collector.
That's a helpful analogy, Victor. So if the execution engine is like a factory, can you explain how these three components work together?
Of course, let's stick with our factory analogy. The interpreter is like the initial processing station. It reads the bytecode instructions one by one and executes them immediately. It's quick to start, but can be slow for repetitive tasks. The JIT compiler is like an optimization station. It identifies frequently used code, called hotspots, and compiles them into native machine code for faster execution. Finally, the garbage collector is like the cleanup crew, managing memory by removing objects that are no longer needed.
That makes sense. Let's focus on the interpreter first. How exactly does it work with bytecode?
The interpreter reads bytecode instruction by instruction. Each bytecode instruction is a single byte that represents a specific operation. The interpreter knows how to translate each of these bytecode instructions into actions that the computer can perform. It's a bit like a translator reading a foreign language word by word and speaking it in your native language.
I see. But if it's translating each instruction one at a time, wouldn't that be slow?
You're absolutely right, Sheila. That's where the JIT compiler comes in. When the interpreter notices that certain parts of the code are being executed frequently, it signals the JIT compiler to step in.
Ah, so that's where the just-in-time part comes from. Can you elaborate on how the JIT compiler works?
Certainly, the JIT compiler takes the frequently executed bytecode and compiles it into native machine code. This process is just in time because it happens during program execution, not before. Once a section of code is compiled, the JVM can execute this native code directly, which is much faster than interpreting bytecode. It's like our factory creating a specialized machine for a repetitive task instead of doing it manually each time.
That's fascinating. It seems like the JVM is constantly adapting to run code more efficiently. Is there anything else interesting about this process?
Indeed there is. Here's an interesting fact. The JVM uses adaptive optimization. It doesn't just compile code once and forget about it. If a method that was previously compiled starts being used less frequently, the JVM might decide to de-optimize it, reverting to interpreted mode to save memory. It's constantly balancing speed and resource usage.
Wow, that's really cool. Now, we've talked about the interpreter and JIT compiler. What about the garbage collector? How does it fit into the execution engine?
The garbage collector is crucial for memory management. As our program runs, it creates objects in memory. The garbage collector keeps track of which objects are still being used and which ones are no longer needed. When it runs, it frees up memory by removing the unused objects. This process ensures that our program doesn't run out of memory and continues to perform efficiently.
That's really important. I can see why it's part of the execution engine. Now, how does the execution engine interact with the other parts of the JVM we've discussed in previous episodes, like the runtime data areas?
Great question. The execution engine works closely with the runtime data areas. It reads instructions from the method area, uses the JVM stacks to keep track of method calls and local variables, and allocates objects in the heap. The program counter, PC register, keeps track of which instruction is being executed. It's a highly coordinated dance between all these components to make our Java programs run smoothly.
Thanks, Victor. That really ties everything together. Now, before we wrap up, let's reveal the answer to our quiz question. Victor, what percentage of Java code typically gets JIT compiled during a program's execution?
Yes, the moment of truth. The answer might surprise our listeners. Typically, only about 3–10% of Java code gets JIT compiled during execution. The exact percentage can vary, but it's usually a small portion of the overall code. This is because most programs spend the majority of their time executing a small portion of their code, often referred to as the hotspots. The JVM focuses on optimizing these hotspots for maximum performance gain.
Wow, that is surprising. It really shows how targeted and efficient the JIT compilation process is. To summarize what we've learned today, the execution engine is a core component of the JVM, consisting of the interpreter, JIT Compiler, and garbage collector. It works together with other JVM components to execute bytecode efficiently, dynamically optimizing performance as the program runs. In our next episode, we'll be diving into the native method interface. Thanks for listening, everyone. If you enjoyed this episode, please subscribe to JVM Internals Crashcasts and leave us a rating. Your support helps us continue bringing you deep dives into the fascinating world of JVM internals. Until next time.
Thanks, Sheila, and thanks to all our listeners. Remember, understanding the execution engine is key to grasping how Java programs really run. Keep exploring, and we'll see you in the next episode.